Welcome to qnawire.
Hi everyone, so what we have is a vertical piston cylinder that has a piston that's resting on a pair of stops. Inside this piston cylinder system we have R134a at an initial mass of 2 kilograms, a pressure of 800 kPa, and a temperature of 80 degrees C. We know that there's 500 kPa that's required to move the piston, and there's actually a valve on the bottom of this piston cylinder system that is opened and then closed when the final mass is 1/2 the initial mass. At this point in time, the temperature is 20 degrees Celsius. What we're asked to find is the total work that's done and the heat transfer during this process. What we're going to write down first is our assumptions. Now, since there are conditions that are changing with time, this is not a steady state process. Next, what we're going to do is we're going to assume that any changes in potential energy and kinetic energy are negligible. Now, using the initial and final states that are given to us, we can calculate and determine several properties. So, for an initial pressure equal to 800 kPa and temperature equal to 80 degrees C, we can determine from our thermodynamic tables that our specific volume at 1 is equal to 0.032659 cubic meters per kilogram. Our specific internal energy, U1, is equal to 290.9 kilojoules per kilogram. Our specific enthalpy at 1 is equal to 317 kilojoules per kilogram. Next, our final state number 2, we know the pressure is 500 kPa, and we know the temperature to be 20 degrees C. Therefore, from this information, we can look these values up in the thermodynamic tables, and we see that our specific volume at 2 is equal to 0.042 cubic meters per kilogram. Our specific energy at 2 is equal to 242.42 kilojoules per kilogram. And our specific enthalpy at 2 is equal to 263.5 kilojoules per kilogram. Now, as we define our system, we're going to choose the tank to be our system, and we're going to do a mass balance. So we can say that the mass entering minus the mass leaving is equal to the change in mass of our system, and this will be equal to M2 minus M1. Now, there's no mass that's entering, so Mi is 0. So we can say that the mass leaving is equal to M1 minus M2. Next, we can do an energy balance and say that the energy coming in minus the energy leaving is equal to the change in energy of the system. And we can say that the work coming in minus the heat transfer minus the energy that's leaving from escaping through the valve is equal to the total change in internal energy of our system. Next, what we can do is go ahead and solve for the volumes at our initial and final state. We can say that initial volume 1 is just going to equal M1 times specific volume 1, and this is equal to 0.06532 cubic meters. Then our volume at 2 will equal M2 times V2, and this gives us a final volume equal to 0.04212 cubic meters. And we can do this because we know that the final mass, M2, is just 1/2 our initial mass. So therefore, what we can do is solve for our final mass and just say that final mass is equal to M1 minus M2. We know initial mass to be 2 kg, so we can say that 2 minus 1 is equal to 1 kg, and that's the mass that has escaped. Next, we're going to assume that the enthalpy of the refrigerant that's leaving the cylinder is equal to the average of the initial and final enthalpies of the refrigerant in the cylinder. So what this means is that we're going to say that HE is going to be equal to 1/2 H1 plus H2. And this gives us an enthalpy of exiting the cylinder equal to 290.23 kilojoules per kilogram. Now, we can solve for our boundary work by saying that WB is equal to P2 V1 minus V2. and this is equal to 11.6 kilojoules. Now, by plugging all of these quantities into our energy balance equation, we can directly solve for Q out, and we get that Q out, or the heat transfer, is equal to 60.7 kilojoules. So these are our final answers.